Okay, so your written test will be tomorrow. And please make sure you got your PPY login tested. Make sure you can log into the E-class and do the dual mobile. Any loss of time, please. I cannot accommodate. So make sure you just try. You can just go to the lab and try it quickly. I think that'll be very useful. Photo ID, if that's on the mobile phone, that's okay for tomorrow. Not a problem. And sketch paper, bring your own. We cannot provide for everybody. I'm pretty sure you will need it for tomorrow's test. And also looking ahead, after tomorrow, you got one more test before the exam. So you will be your programming test number 2. So by the end of your test tomorrow, I'll also make sure I release the guide for the programming test. But I think doing your assignment number 2 and 3 for the programming part is the way to go. All right. Anyway, let's do today. We gotta stay away from the test contents. We gotta keep covering some important topics. Okay. All right. Let's do a quick recap. Can you please maybe shut the door at the back? Thank you. Yeah. So everybody can be more concentrated. Yeah. Thank you. Thanks so much. All right. So let's do a quick recap from Monday. So we introduced the idea about DAG, directed acyclic graph. All right. So you just got to remember about the definition. First of all, it's a graph. You got vertices, you got edges, it's directed, it's not undirected, it always got direction, okay? And direction usually suggests about dependency. So whenever you want to decide whether you should really model your graph as a DAG, think about if there are any dependencies existing among the objects in your application. And also there's no cycle. No cycle, in that way you don't have any circular dependency. I think that's also a very important design decision you have to make. And also you can make a comparison between DAG and also tree. Of course, for tomorrow, you have to be sure you are also familiar with all the concepts we talk about. Of course, it's only 1 hour test. I cannot put everything in the 1 hour test. But I would say for you, the safest bet, just study everything, right? You will see which one you will get tested. And once you get a DAG, which is a nonlinear structure, so this will be a very typical one, just doing like a prerequisite structure for your courses. And then we have something called topological order. So thinking this way, you're given the input, a DAG, which is nonlinear. There should be some algorithm, which we talk about, which is called topological sort. It's going to turn the nonlinear structure into something that's linear. And the way to do it is by modifying slightly the depth search. We'll see later today why breadth search in general cannot be used for this dependency sorting purpose. You just cannot. Okay? All right, we spoke about you should really try to find out the edges and see how they're reflected, in a pair of vertices in the sequence. And we also work out this logical expression. All right, so guys, you want to, when you study later for this part of lecture for the exam, you really want to dive deep into the formula over here. I might test you something about it. Exactly what, I'm not too sure. You want to understand about this formula, right? For example, right? Here, I have a legal order, right? Think about this exercise here. Let's say I got 10, 11, I got 20, let me say a little bit easier for you to see. I got 10, 11, I got 10, 21. This is legal. What if I swap the order? I put 10, 21 followed by 10, 11. This will immediately make this order illegal as far as the DAG is concerned. So now here's a question for you. Given this particular new change, how can you argue it is going to make this universal quantification to be false? Can you justify it? All right, so that would be some exercise for you to think about. All right, so that's something I'm just trying to give you some direction about how you can play with what we discussed in the class and make some slight extension to exercise. And of course, given that you already studied for the math review lecture, this one shouldn't be too difficult. Think about how you can really make a universal quantification actually not true, right? All right, think about it. And then we spoke about, okay, that's just legal orders. And then conceptually, we're going to do topological sort, which is going to be based on depth search. All right, so very quickly about this page here. So this one just showed to you how the algorithm can be run. You can feel free to give it a try in Java. Even though it's not part of the assignment, I think beyond this course, whenever you want to build a graph for yourself, very likely you have to implement depth search and make some modification. I think topological sort is a very nice way to exercise about what kind of changes you can make. It's not a lot of changes, but you can really achieve something very useful. All right, the running time is going to be the number of vertices plus the number of edges. The insight is, because it's based on depth first search, you're going to push and pop every vertex only once, right? You never try to push and pop one vertex and try to push pop again. You don't do that, right? Only once. And also for edges, in the case of directed graph, we try to identify each edge as a back edge, forward edge, cross edge, or discovery edge. Only one of these. Once you identify the edge as one kind, you never try to overwrite the identification, right? That's why it will be proportionate to the addition of these two. And I think maybe Diago also suggested another important insight. What if the graph is relatively complete, right? In that way, we know that the number of edges over here will be approaching to number of vertices squared. In that case, this is going to dominate over this. Asymptotically, it's just going to be n squared. However, not necessarily all the time. You have to know what the assumption you can make about the graph. Okay. All right, that's about running time. You guys can take a look at the highlighted parts, which I also tried to explain last time on Monday. All right, so that's the mechanical process we try to get used to. It's basically depth first search, but you just want to be prepared. In order for you to really cover all the vertices, you may have to run multiple runs for the depth first search. So for example, depending on the stop vertices, really, if I start from here, this will be the first depth first search I can have. Right? And then if I start from here, I can cover another two vertices. If I do another one here, I can cover another one. So I got 1, 2, and 3. DFS trees. Tree number 1, tree number 2, and tree number 3. Right? So in the case of the directed graph, that would be something you gotta be aware. So not necessarily you start with some arbitrary vertex is gonna cover all the vertices. Not necessarily. So this is exactly the point you want to note. Right, apart from that, you just have to make sure you accumulate the order along the way. Every time you want to backtrack or pop off a vertex from the stack, you want to insert at first. So you're creating a reverse order of the backtracking. Right? So that's something you want to know as well. Okay? Any questions about running topological sort in general? An easy question for the exam will be, I simply give you a deck and say, okay, let's now try to follow through maybe a certain order of the stop vertices, and now I want you to give me this topological sort accordingly. That'll be an easy question. At least you can do it mechanically, right? Another kind of question you might expect would be, I might just give you some application question, and to really solve that application problem, you will need topological sort. So the one we kind of started with on Monday about transactional updates, it's just one kind, right? Let's now continue with it. I do want to finish that properly, okay? Okay, let me start with, oh, by the way, so there's another example here. You can feel free to give it a try, right, over here. Right, just a different deck, slightly more complicated. You can give it a try and see what kind of topological order you can figure out. There should be multiple legal ones, not necessarily just one. All right, so let's now start with this, okay. So this is the input. We're given constraint, logical constraint. If I come here, the logical constraint, we say that they commute. Doesn't matter the order. We're simply saying, so notice the difference. Whenever we got some transaction, which means by a single transaction, we're gonna execute multiple updates at the same time, like a parallel, right? Parallelism is what we are dealing with. And before the transaction, we got all the variables, A, B, C, D, and to really know the difference, after the transactional updates, all the variables are prime, A prime, B prime, C prime, and T prime. Conceptually, it should be very clear about what A versus A prime really mean before and after the updates. And for you to really specify the intent, you simply say, for example, C prime here, the post-state value should be exactly equal to the combination of B prime, A prime, and D. So that will be B prime, A prime, and also D, right? So there will be like a mix of the pre and post-state value. There will be some dependency amount here I want to walk you through. Before that, I want to show to you what if we didn't try to solve this properly? How wrong can it be? Let's see that, okay? And then we'll try to appreciate how topological sort can really resolve this issue for us. We'll revisit this page very soon, okay? Let's go back here, okay? Let's see this example here. So this part here is simply just the same updates. Right? I just copy that. Okay? Let's assume this. The pre-states, A will be 1, B will be 2, C will be 3, D will be 4, right? Somehow, in the last part of Monday, I try to walk you through about how you can figure out the prime value for each variable, right? The order I went was, okay, let me just go again. I kind of say we started with D prime, simply because it only depends on the pre-state value without any post-state. So that one there is really self-contained. We can start with that, and so on, right? We try to figure out A prime, B prime, C prime, and D prime. So guys, for this part here, I'm gonna skip, right? That's something we discussed on Monday. If you're not exactly sure how to figure out the correct post-state, you can look at Monday's video. But let's assume that's the case, okay? And I forgot to put also C prime here, okay? That's my bad from Monday. I'll put it down, okay? What we want to see now is to see how badly things can go. Okay, so this will be 84, right? 84, that's what we calculated. Okay, so now here's what we have. Given the pre-states, and we have this parallel constraint, this will be the corresponding correct post-states. All right, so now, let's say without using a proper solution like a topological sort, how would things go? Okay, what I did was, I have a very naive implementation strategy for this constraint here. I simply use a variable assignment. You can think about it like an equal sign in C or in Java, but I put colon equal just to explicitly say that's variable assignment. And for variable assignment here, they do not commute, which means I have to execute this, and then execute that, and then execute that, and that. There's a particular order, right? I just follow the same order. I simply say C here, I just get rid of prime, will be B minus A plus D, right? That's what I did, right here. Let's take a look at what's going to happen, okay? So let's try to evaluate this. So we know that over here, B over here will be 2. And A here will be 1. And then D over here will be 4. 2 minus 1 plus 4 will be 5. So you can think about this value over here is C prime. You can see that as soon as we have done this, because this is the only time we are trying to assign something to C. But if we're going to get 5 as opposed to 84. It's already gone wrong. See my point here? Okay, I wouldn't dive too much into it, but let's do one more, and then I can let you do the rest. Okay, let's do one more. And here, I'm trying to say, B here is going to be A times D. Okay, A here is going to be, again, 1. And then we're going to get D here is going to be 4. Okay, 1 times 4, we get 4. Right, you can see 4 here is also completely wrong, rather than 9. Right, so far we got 2 wrong values already. Let me do one more. Okay, I do want to point out something to you. Okay, and then over here, when we do A here will still be the value here. That will be 1. A hasn't been changed so far, right? And also C here, notice here. If you look at the original specification, C here, this is the pre-state value. Because C here is unprimed, right? That means as far as the specification is concerned, C here really means the pre-state value 3. However, in the implementation, we have something totally different. In the implementation here, C here is not the pre-state value. It is the C updated so far. What would that be? 5. So 5 here and 3 here, they also mismatch. Okay? I think that's good enough for us to see. If you simply try to just get rid of all the prime and just turn equal sign into variable assignment, it's not going to achieve what you want. That's the main point, right? Of course, there are different ways you can mess up with the post-state value. This is just one way, right? So in the exam, what I could have done is I can give you the pre-state value over here, and then I'll give you the left-hand side right here. And then I'll give you some potential implementation. You're going to argue to me whether or not this implementation here is correct. So the way to do it is, number 1, based on the constraint and the pre-state, figure out the corresponding post-states. Of course, you have to somehow figure out manually which one you should really evaluate first. right? You may kind of sketch some topological sort on your paper, which I'll show to you, right? So you want to do that. And then compare with, if you simply try to execute the programming assignment one by one and see if the value will just match. If it doesn't match, it's not a good implementation. All right? So that's a little warm-up exercise I want to do with you, just to say without a systematic way to solve this, you're just going to mess up all the post-state value. Okay? Okay, let me just write a conclusion here, and then we can move on to solving this properly using topological sort. So this is wrong implementation. Not all the post-state values are correct. As long as you can mess up with at least one post-state value, it's not correct. Okay. All right, you can think about this example here. You can create some of them on your own. I think that will be useful. Okay. Now, let's come back here. Now, how do we solve that properly? Topological sort. In order to do topological sort, because we want to sort out the dependency between the variables, maybe we should evaluate D first before we can evaluate C. But how do we know that, right? In order to do topological sort, we have to build a DAG. In order to build a DAG, we have to know what does error really mean in that particular DAG, right? So that's a logical argument I'm trying to make to you, right? I'll write it down, and then we'll figure out the DAG. So what we decide is somehow we have to do topological sort. In order to do it, we have to build a DAG. And in order to build a DAG, we have to know the meaning of an arrow. Meaning of an arrow for dependency. All right? This will be a very important design rationale that we are following, right? It's even before we get to the actual solution. Let's figure out the arrow over here. Let me give you guys two choices. You tell me which one makes more sense, okay? Let's say over here, you can see, let's say here. Let's say, for example, if you talk about this one here, just for example. So here we're saying, in order for me to the post-state value of B prime equals to the post-state value for A and the post-state value for D. Right? So let's now figure out the dependency. Let's only look at maybe B prime and A prime, only these two. All right? So now I'm looking at these two, and then I'm asking myself, what should be the dependency? All right? And I'll put a star here. Okay? And then I'll put a star here. Let's figure out two choices. Either you can say B prime here, and then we have A prime over here. And another one will be the opposite. We got A prime here, and following that, we got B prime. Okay? So guys, don't lose the big picture. I'm basically considering this part of the input. Based on this part of the input, should I construct this direction here or the opposite direction? Which one? Just before you answer, okay, just before, I want to also give everybody just one more hint, right? That's something you want to also recall. We said earlier, on Monday, we say that whenever you got an arrow, that really means, for example, let's say here, we got V and we got U, and then we got a direction. Conceptually, always the case. V here must happen before U. So we're asking the same question. Should B prime happen before A prime? Or should A prime happen before B prime? So you're suggesting maybe the second one will be the one to go, right? Do you guys agree? All right? Because you think about conceptually here. In order to calculate B prime, we must first of all calculate A prime first, so we can use its value. All right? It's a very important decision to make, so this will be the way to go. Okay? So this one is saying, evaluate A prime first, and then evaluate B prime. Guys, that's a very critical step. Any questions about this? Okay, once we have decided this, we should be able to build a DAG. Okay? We want to build a DAG. Specifically, all the vertices is going to be the post-state value. Pre-state value, I have another way to handle. Don't worry, I'll mention that to you. That one's outside the topological sort. Let's only worry about the post-state values. So let's say the V will be A prime, and then B prime, C prime, and also D prime. Right? So all the post-state value for this example. So we got 4 vertices. How can we build a DAG accordingly based on our understanding that this one here should be the way to go? All right? Let me start with one with you. If I look at this one here, right? That would mean A prime should go before a B prime. Only these two. So that means I'm going to get A prime should go before B prime. You might be asking, why did you draw it vertically? Because I want to align with the actual nice, pretty printing of the graph. Of course, you can draw whatever orientation you like, right? So A prime should go before B prime. And then D prime should also go before B prime, right? So we also got D prime. Right? Okay. And then let me now try to make it more visual for you. Okay. Give me one moment. Let me erase the color right here so you will see exactly how to see that. Okay. So the one we just did, this arrow here, and this arrow here, and also this arrow here, correspond to basically this, this, and that. Right? So A prime should come before B prime, and D prime should come before B prime. Right? What about here? C prime. What should come before C prime? B prime and A prime. Okay, good. So all we should do is, let's now work out C prime. So C prime, let me put it here. Both B prime and A prime should come before that. B prime should come before that, and also A prime should come before that. Those are the yellow dependency. All right? Let's go on. What about A prime? What should come before A prime? B prime, right? And the pre-state value, don't worry. We only worry about post-state value. So what we have is, so D prime should come before A prime. So that means we're going to get just another arrow over here. What about D prime? Should anything that's post-states come before D prime? No, because as far as the constraint is concerned, the right-hand side has only A and C and 5. No post-state value, no prime. All right? So this is the DAG that corresponds to the input. So the very spirits, the very critical bits about solving this problem here is, given this constraint over here, number one, decide what arrow really means. Because if you simply got B prime and the A prime this way here, you just got everything wrong. Then the sorting result will just be wrong. All right? First of all, decide what arrow really means, and then turn this input here into a DAG. And then we're now coming into our comfort zone to do topological sort. All right? So what's good? Okay, let's now topological sort. Let's now do it the easier way. Let's say somehow I choose the star vertex to be D prime. In that way, I will be able to cover just by one DFS run, right? Let's say I choose it, okay? So what I will do is let me do topological sort. Topological sort. Okay, so what I will do is I'll run a DFS topo. And then I will start with D prime, right here. D prime, and then I got empty list to start with, right? That's completely mechanical, like what we did on Monday, all right? Let's just dry run that a little bit. If I got D prime here, and then I should really go to A prime, and then I go to C prime. Oh, sorry, let me say it again, I got it wrong. First of all, I start with D prime. First of all, I go to A prime, and then I go to B prime, and then I go to C prime. Done, I cover everything. So these two are not discovery edges. What edges should they be? That's something you should know for tomorrow, right? Okay, hopefully you will review that. All right, let's now do some documentation for you, okay? If I try to stack right here, I start with D prime, and then I go over to A prime, I go over to B prime, and then go over to C prime. And then as far as C prime is concerned, nothing else, right? And then I got push and pop, right? Let me put it here as well. Okay, let me say push and pop. Push and pop. So it's going to be D prime, A prime, B prime, and C prime, right? And then the order to backtrack will be, first of all, C prime. So once I got rid of C prime, and then I go to B prime. And for B prime, you can see the only vertex over here has been visited already, nothing else to be handled, right? And etc. Okay? So the pop order will be just C prime, B prime, A prime, D prime. All right? So the final topological order will be just the reverse of the pop, which will be D prime, A prime, D prime, and C prime. D prime, A prime, B prime, and C prime. And this is, again, the reverse of backtracking. Follow so far? It's about performing topological sort. And we got this order here. And by the way, if you later on went back to what I did on Monday, the order in which I figured this out, the correct post state, correspond to exactly this order. There's no magic because I did the topological sort myself first, so I know how to go over that. So if you are given something similar, you have to do something similar, like what we did here. Well, we got a topological order, and then what? We want to figure out some good implementation. All right? So here is the implementation. You can verify it, but I'm going to put it here for you. So the correct implementation goes like this. Correct implementation. Okay? Let me call that stage 1, stage 2. Stage 1, I'm going to store all the variables as of now as a pre-state value. Okay? So what I will do is I'm going to say something, I just use a convention. Let's say old value, or let me say pre. The pre-value of A will be just the A right now. And also the pre-state value of B will be the B right now. And the pre-state value of C will be C. Pre-state value of D will be D. Okay, stage number 1. Once this is done, I'm now going to follow the topological order for the prime. And then for the right-hand side, whenever I see prime, just use prime. Whenever I see unprime, use the pre. All right? Let's now use a different color for that. Let's say for D prime. So I'm going to say D prime will be equal to pre-state, and 5. It's going to be pre-A plus pre-C plus 5. Okay? And the next one, A prime, is going to be the pre-state value of A and D prime. So now I'm going to say A prime will be equal to, I can say pre-state of A plus D prime. Right? But even better, I can simply get rid of the prime. How come? This statement here is executed after this one here. So when I refer to D right here, it's really referring to the D after the change. So that's indeed D prime. I just did it in the right order. Okay, think about that inside, right? May not be 100% for the first time, but you do see the big picture. Okay, all right, 2 more. And then we got B prime. So I'm going to say B here will be assigned, B prime here will be A prime and D prime. A multiplied by D. Right? So A and D here are what we have updated so far. So A here is indeed the result from this. And D here is indeed the result from here. Right? Indeed A prime and D prime. Finally, we have C prime. So it's going to be B prime minus A prime plus D. So C will be B minus A plus the pre-state value of D. You can double check this one here. If you try with the correct pre-state value here, you're going to get exactly this. So we did it in the right order, and also we correctly cache the values for A, B, C, D before we start the updates. All right. It's a tricky example, but I'm just trying to show to you some very practical application for topological sort. Right? Usually, when people implement compiler or any program that's going to try to implement or linearize the parallel constraint, topological sort is just a standard solution. That's why we cover that. Right? Okay. Guys, any question? Yes, please.
What are the algorithms stopping us from going like D, B, C, and then having to backtrack to get back to?
Oh, in that way you have a cycle. In that way, you cannot really use topological sort because you cannot really build a DAG. Remember, DAG should be acyclic.
Yeah, but I'm saying like when we're doing the, we go D, then A, then B, then C.
Yeah.
But what's stopping us from going D, then B, and then being forced to go to C from there, and then having to pop off to get back to D and then go to A?
I don't follow you. Say that again.
Like, why do we go to D to A instead of D to B? D prime to B prime, sorry. In the graph.
Are you suggesting another order?
How do we know that's the correct order?
Because this order here, right, we are following this order, right? And this order is the result of performing a topological sort.
Yes, but in the topological sort, how do we know to go D prime to A prime and not D prime to B?
Maybe you missed that Monday lecture, I guess, right? That's okay. Let me mention briefly. So we're given this stack over here, right? The way to do topological sort is by doing a depth search, basically, right? So we go from D prime, and then we go to A prime, and then go to B prime, and go to C prime. At this point, we are supposed to backtrack. So topological sort basically will give you the reverse order of backtracking the vertices.
Yes, but the reason we go D prime to A prime is solely alphabetical, right? Like, why not go D prime to B prime? We can also do depth search that in the first direction is arbitrary.
Right. So if you actually try another, well, I see what you mean. So here, of course, we're assuming that we are visiting the adjacent vertices, maybe by the alphabetic order, but we're still doing a depth search. If you somehow, for example, let's say you want to go to D prime and then B prime, I see exactly. Okay. If you do that one there, it will still give you the valid topological order. I can write it down maybe for next class and say. Okay. I'll write it down first. Okay. Yeah, it's a good point. It's a good point. Your fellow student point goes like this. What if we try to go D prime, B prime, A prime, and then C prime?
Well, no, because A prime has to go towards B prime. So
Oh, beg your pardon. So if you go D prime, B prime, and then C prime,
yeah.
right? I think in that way it will still work. Let me write it down, maybe for next class, okay? Yeah, I'll put something here. I totally see your point. what if visit B prime first and then A prime? So the short answer is you will still get a valid topological order. So you're still doing a valid, like a that first search, it will still work. But let me write it down maybe for next class so everybody will be clear. Okay, that's good. One more thing I want to clarify for doing a topological sort. Okay. So the way we kind of show that is we are using a modified version of the that first search. Okay. However, we want to show that if you do like a normal breadth first search, it's actually not the way to go, right? We'll just use some simple example there and then you will see. Okay. So let's say we got a graph right here. And then we're going to compare how doing a depth first search versus breadth first search and see how things will be a little bit different. So we start with S over here, and then we go to A, right? And then we also go from S to B. And then B to A. All right. And maybe on this end, we're going to consider breadth first search. Okay. And for the same graph, we're going to try maybe the depth first search modified version for topological sort. And for this part here, we're going to do the depth first search and then topological sort. Okay. Let's do the topological sort first. Right? That's something we are familiar. Let's do that one first. That one there, again, we assume we do alphabetic order, right? So what you raised there, I'll give that alternative version next Monday. Okay. So let's now start with S, let's say, over here. And then we're going to get push and pop. Push and also pop. S, oh, let me also put a stack right here. Okay. So we got S, and then we got A, right? S and then A. Once we get to A here, you can see nothing else to go any further. So we're going to push it off. We're going to pop it off. So A here, and then we go back to S. And for S here, this one has been handled, so we go to the other way. And we go to B. A, B. So once we go to B, you can see that the only incident edge, that one is actually more like a not discovery edge, because it's going to something that's already visited, so nothing else to do. So we're going to backtrack B as well. Okay. So B has been pushed, but since we cannot really go any further, so we are going to backtrack as well. Okay. And finally, we go back to S. Both incident edges have been handled, so backtrack S. Okay. So the way we are trying to handle this is really like this. Okay. So the topological order is going to be S, B, A. S, and then B, and then A. Right? So that's correct order. Okay? Let's just make some notes. And the inside over here wouldn't apply to the breadth first search. Okay? The inside really is when we are doing A right here. Okay? When we are here, we are really trying to see if there's anything else that A will depend on. In that case, we should really do them first before we do A, right? In that case, we are not really, let me just say that here. When A is when A backtracks, all the outgoing edges of A have already been handled. Okay? So that means the dependency beyond A have already been handled, so we don't have to do anything more. Dependency beyond A is sorted. So no need to go further. So that's really the nature about backtracking. You have to make sure every time, if you cannot really lead any further from the current vertex, so that means no further dependency should be handled. In that case, you can remove it from the stack. However, the way we're going to remove a vertex from the queue is not really following this kind of insight. It's not really. You simply go with the order that we decide to in-queue. Okay? It's a little bit different. Okay? So keep this one in mind. It really explains about why that first search will be the way to go. Okay? Backtracking. And this one here does not apply to breadth first search. Okay? Let's just see some simple example. Again, we're going to start with S, the start vertex over here. Okay? And then we're going to do in-queue and DQ. So we got in-queue, and also we got DQ. Okay? We put S here. So this will be level 0. Okay? And then, in this case, we're going to, let's say we go with alphabetic order. So we're going to in-queue A and B. So they will both be in level 1, right? That's that breadth first search. So this will be our level 1. And then we go with A and B, right? So this will be discovery edge. This will be another discovery edge, right? And now think about how exactly do we DQ, right? As soon as all the incident vertices, as soon as all the incident edges have been handled for this particular vertex, we simply DQ that, right? So we put S, put it out of the queue. How do we decide about A and B? It turns out we're going to see we cannot really go any further. This will be the front of the queue. You cannot reach out to any further level. In that way, we're just going to DQ it, A. And then when we get to B over here, of course, this will be a cross edge. And we can also not extend any further to any further level. Not the case, so we also DQ it, A and B. Now here's a critical insight. Before, we have to somehow backtrack A. It's because we have no further extension possible. But here, we go with the order. It's really to do with the in-queue order, not to do with any backtracking. The order here only reflects how we visit adjacent vertices, which will be alphabetic order, which it will be alphabetic order, which means no dependency is considered. Okay? So the main comparison is just to see when you try to do the depth first search version, backtracking A and then B has a reason because we actually have a dependency over here. So that's why you got to do A and then B. On the other hand, in this case, we're dequeuing A and B. It's not because of any dependency, which is about when we actually try to in-queue them into the queue, we simply follow alphabetic order. Nothing to do with dependency. So the conclusion is, when you want to sort out, to implement topological sort, you just cannot modify the breadth first search and then try to do it. That's why. Okay? A little bit tricky here, but think about that comparison. Okay? Okay, we're running a little bit longer than usual, but I think we should take a break. So I just want to finish this part here to go thoroughly for topological sort. Okay? Not for topological sort. All right, any questions? So for topological sort, when you review this part of the lecture, understand the definition for DAG, and understand how you can do topological sort mechanically based on depth first search, and also given application like a parallel constraint, how can you turn that into DAG and then do topological sort. And finally, understand why modifying breadth first search will not give you the dependency sorting that depth first search will give to you. All right, so these are the critical points you want to review and get convinced. All right. Why don't we take a short break, and then we're going to cover new stuff. Okay. All right, so now we're going to start with slide number 82. So we're done with the topological sort. The next one will be minimum spanning tree. We talk about spanning tree, but let's now talk about what does it really mean for a spanning tree to be the minimum. Apparently, you got multiple spanning trees to compare, but what will be the minimum one, right? But I'm going to go over the points with you, so don't worry. I'm going to give you some roadmap about what we're going to cover. It's going to take today and for sure Monday and possibly mostly next Wednesday as well. We're going to learn about minimum spanning tree problem. We're going to learn about the so-called greedy algorithm. So Dijkstra and also minimum spanning tree algorithm are instances of this. So we're going to learn about them carefully. And then we're going to see some tracing for the algorithm. And we're going to see some argument about the correctness for the minimum spanning tree. The algorithm itself is very easy to trace and execute, but to really argue about its correctness is much more complicated. In some way, that's a good thing, because for you to apply the algorithm, it's straightforward. It's really when you want to argue about its correctness, you should be more careful, right? So we sort out both concerns. Okay. So it's going to take from, this will be the algorithm. We'll see, we'll work out one example either today or on Monday, and then we're going to see some ideas about partition, cluster, and cut, etc. Right? Most likely we'll get to this part here on Monday, or later part of Monday. But one thing at a time. So today we're just going to see how we can understand the minimum spanning tree problem. Okay. So now I'm just going to deviate from the slides, and then we're going to work on the iPad. Okay, to take some notes. Okay. But I might add a little bit more before Monday, but I'll let you know. Okay, let's look at the minimum spanning tree problem. Input and output. So this will be the input, which will be some kind of graph. We're going to make some assumption about the input graph. And this will be the output, which will be a spanning tree. However, the spanning tree we're going to return is going to satisfy a certain property. But let's not define. Okay? First of all, let's start with the minimum spanning tree. How do we represent it? This is something I also briefly described when we talk about how you can adapt, like a depth first search or breadth first search, to really answer some graph question. One of them is actually about spanning tree. All right, so that's kind of related. Okay, I'll get to it. Also a little bit more concrete today. Okay, minimum spanning tree, you can say, think about it like a capital T, like a set. And T here will just be a set of edges. Okay. I'll elaborate more details about how exactly it could look like. But let's talk about the input. We have some assumption to make. So for the input here, in order for you to calculate or compute the minimum spanning tree, the graph has to be simple, undirected, and also weighted. So these are the three. Okay? It should be simple. And I'm pretty sure you will recall the definition for what does it really mean for a graph to be simple, right? That's what when we talk about first, introducing graph. I'll leave that to you. Also, it should be undirected, unlike DAG, right? We'll talk about another kind of graph. Undirected. Also, weighted. Weighted in the sense like a Dijkstra algorithm, right? You have the weights associated with each edge, right? And when we talk about the weights, for example, let's say here. So when I talk about weighted, if you look at the number, for example, here, I got, let's say, a flight map. I think we have seen something very similar before, right? We simply got the flight map of some airline company. So we got different destination, for example, Boston, and then we got San Francisco. And the weights for the edge is 2,704. It's like a unit for distance, right? It's like a cost. Okay. So for each weight over here, typically it can mean two things. It could mean the cost, or it could mean the benefits in general, depending on how you want to phrase it. But I think in our case, since we want to find a minimum, you definitely want the cost to be minimum. You don't want the benefit to be the minimum. Benefit should be maximum, right? So in the cost case, it should be about minimizing it versus maximizing the benefits. So for our case, we definitely talk about the cost. We want to make sure it is the minimum. Okay? So we're going to stay with any number we'll see later. For our example, the number there simply means the cost. So that's why we can apply the minimum spanning tree algorithm. Okay? And then let's now review some terminology here. Okay? So just to start with, a tree. Okay? In our case, the tree will be undirected. Yeah, in the interest of time, I wouldn't let you guys to record the definition back to me, but that's something you definitely should have been aware, right? So these are the terms. That's for the basic graph. For tree, it's going to be undirected, acyclic, no cycle, and also connected. And of course, this part over here about undirected and acyclic is about what a forest is. So we know the difference between the forest and the tree is about connectivity, right? And of course, the tree itself is also a subgraph, satisfying certain properties. Subgraph, right? Now, spanning tree is a tree that will be spanning, that's going to cover all the vertices. Also, we talk about spanning tree. Spanning tree. First of all, it has to be a tree. And also, it must be a spanning subgraph. Okay, we're moving from subgraph to tree and then to spanning tree. And we're going to move on to minimum spanning tree. That means, let's say here, in this input graph, right? How many vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9. What should be the size for the spanning tree? How many edges? Is it arbitrary or it should be a fixed number? It should be, well, when you got a graph, if that's connected, in order to get a spanning tree, the edges should be exactly number of vertices minus 1. Right? That's a basic property we've been saying so many times, right? Just keep that in mind. So now, here's a question, right? In order for me to get a spanning tree from the input, I need to choose 9 minus 8. Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 minus 1, 8 edges. Is there only one way for me to choose 8 edges that's going to create a spanning tree? Not the only way. For example, this is one way, right? On the other hand, if I actually try to say I get rid of this particular connection, maybe I can put this connection instead. I can still keep it like a spanning tree. So there are more than one spanning trees available for this particular graph. There are so many spanning trees. Now I'm going to choose the one whose edges will add up for their weights to be the minimum, because we interpret the weights for the edges to be cost, right? So that's the idea for minimum spanning tree. You want to understand for the graph that's being connected already, you have to make sure you can find exactly the number of vertices minus 1 edges that will be spanning. Okay? Okay, let's write this down. Minimum spanning tree. Minimum in terms of the cost. Okay? With respect to the cost. So minimum spanning tree. We are basically saying when you add up all the edges in the tree, it's going to be the minimum. Okay? So you will see this notation as well in the slides. We say the weights for the tree, the spanning tree, right? We talk about T. Okay? it would be the summation of the weights for all the edges. So for all each edge, U and V, that's in T. And then we're going to sum up their weights, U and V. Okay, let's understand this formula very quickly, just in case you get lost. T here is a tree, spanning tree. Spanning tree is understood as a set of edges. So we are saying that for every edge, U and V in the tree, we're going to sum up their weights all together. That value there is going to be the weights of the tree for the spanning tree. I want this weight to be the minimum. Whatever spanning tree that's going to give us the minimum is going to be the minimum spanning tree. Okay? So again, the T here will be collection of edges. And over here, the W here, the result, should be the minimum for a minimum spanning tree. Every spanning tree can calculate the total weights, but for the minimum spanning tree, the weight should be the minimum. For this particular input here, the spanning tree that's going to give you the minimum summation of the weights will be this particular spanning tree. I already annotated beforehand, right? So this one here, let's just write it down, okay? And also I do want to make a point, which could be relevant later. So let's say, for example, for the output right here, okay? We have a minimum spanning tree, and we're going to see exactly how to calculate it algorithmically later. It's going to be a set of edges. Right? Since we've got 9 vertices, so we got exactly 8 edges. So the number of vertices is 9. So the number of edges in the spanning tree will be the number of vertices minus 1, which will be 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? It's a tree spanning, and also exactly number of vertices minus 1. Okay. Let me just write it down. And then I do want to make a point related to implementation. Okay. So you can see here, I got from, let's say, Boston to JFK. Boston to JFK. Another edge. So from PVD to JFK. PVD to JFK. Okay. Okay, one more. From JFK to BWI. JFK to BWI, right? And so on. There will be 8 edges in total in this set. So now in Java, how do we implement this? It's a set. Each member in the set should be an edge object. Okay? That's the point I want to make to you, and could be relevant to maybe your programming test that's coming up. Okay? So for this part here, you ought to think about how you can implement this in Java. So this will be maybe a hash set of 8 edge objects. Right? It's going to be a hash set. And now, question for you. If I'm doing a depth first search or breadth first search, I want to find like a spanning tree. What kind of edges should I add in to the spanning tree? There's so many kinds of edges. Which one should I add in? Anybody? We got choices. Let's say we're doing a depth first search on undirected graph, right? We can only get discovery edge or back edge. Yeah, discovery edge, right? That's something we said earlier. That's why discovery edge is also called tree edge. Okay. If you want to construct this hash set over here, somehow you have to figure out exactly the discovery edges is going to make the minimum weights ultimately. That's something we'll see. But in order to just get a spanning tree, not necessarily the minimum, you can just collect all the discovery edges when you do the traversal. Right? It's a point we actually made earlier. I'm just trying to repeat it to make it more context over here. Okay? Right, so that's about the basic definition. Okay? And then we're going to do a little bit of, I think we'll talk about the actual computation for minimum spanning tree maybe on Monday. We can start you fresh. But just go over some concept over here. Take some notes right here. So greedy method, okay, or greedy algorithm. We'll see two examples in this course about greedy algorithm. So greedy method. It's more like a paradigm for algorithm, iterative typically, and then so the conceptually is very simple. You just have to see the different steps in the template and then see how your algorithm, why it is a greedy algorithm. There's something you can actually see, but I'll show to you. Okay, so greedy method is just a paradigm. This is a paradigm, and we got two examples. Example number one, the Dijkstra algorithm that we did earlier is actually a greedy algorithm. I actually didn't say that at that point, but it is. So the Dijkstra algorithm, which is about the shortest path. You can think about the length of the path is the cost. We want to find the total length, that's the minimum. But in some way, it's more like a greedy algorithm. We want to find something that's optimal. Another one, which we'll see for the minimum spanning tree computation, is called Kruskal's algorithm. Just another name, really. Kruskal. And that one there is for you to calculate minimum spanning tree. Right? So these are the two. We'll see. Okay? We have already seen Dijkstra. We'll try to see later on Monday to see all the ingredients that we're talking about for greedy method. Dijkstra simply satisfy them. We'll clarify that first, and then we'll see how the Kruskal also will satisfy that paradigm. Okay. Let's now just see what the ingredients are. Okay. First of all, greedy method is a design method for algorithm. It's a design method for algorithm. Okay. Number two, it is an iterative algorithm. You don't do it recursively. Okay. Step by step. Iterative. Construction. Okay, I just write it down and then we'll go over. Construction of some complete solution. And here the complete solution is something we'll see. The complete solution is supposed to be globally optimal. For example, we want to minimize about the total length of the path to be the true shortest path. So the complete solution, ultimately, when the iterative algorithm terminates, is going to be globally optimal. So this is our goal. However, for individual iteration for the greedy algorithm, you are somehow going to choose what looks to be the cheapest for you right now. And somehow magically, it can just work out globally. That's something we'll see. Okay? But I'll write it down. Okay? So this will be the first ingredient. It's going to be step by step. And then we're really trying to calculate something globally optimal. Okay? And let's now talk about from each individual step or iteration. From each step or iteration. Okay, there are three things we want to watch out for, right? Three things related to what kind of work should we do between the iterations, right? Number one, there will be multiple, we call choices available to you, right? Let's say, for example, in the Dijkstra algorithm, you got so many vertices in the priority queue. You got so many choices, but which one should you pick? There's got to be some criteria, right? So, number one, multiple feasible choices exist to extend the partial solution so far. To the partial solution so far. We're building something. Ultimately, once you finish all the iterations, the solution will be complete. But as you walk through the way, for each iteration, you're just completing something partial. Okay? So here, the keywords is about multiple. You must have some criterion about how you can pick the choice for this iteration. Another thing is, which we'll see in the later bullet point, once you pick the choice, you never regret the choice. You never have to. For example, in the Dijkstra algorithm, once we process one vertex, we remove it from the priority queue. Do we ever put it back? Not really. That's also another spirit for the greedy algorithm, right? Once you made a choice, you never regret. Okay? You don't backtrack, basically. Okay, and then the next one. Pick the choice that is the best or cheapest right now. So when I say right now, I really meant as far as the current iteration is concerned. We don't worry about any previous or next iteration, just right now. We only focus on now, right now. With respect to a so-called cost or score function. Okay, so here I just need to branch out quickly. Okay, we'll talk about something called a cost or score function. Right? Let me talk about it very quickly so you get an idea. Okay, every time you got so many choices, you want to pick the one that's going to work just for this iteration. You got to have some quantitative, like a measure for you to judge. Okay, so here, I'm just going to write it down. Okay, okay, right here. So when we talk about the cost and score function, okay, and specifically, we are trying to minimize the cost. And for example, the capital D value in Dijkstra before I write any points down, let's think about this, right? For Dijkstra, you have seen that already. Every time we actually want to pick something from the priority queue, which one do we pick? We got so many. We pick the one that has the lowest capital D value and then process that. Once we have processed that vertex, we remove it and never put it back. Right? So the capital D value is the measure for us to see the cheapest way to go forward. Okay? It's going to help us rank the choices. So rank the choices and also help us measure our solution to see what's the total length so far, right? May not be the ultimate just yet, but we are moving in the right direction. Partial solution so far. So these terms, I think I just want to mention them so you can see that in general, if you want to design a greedy algorithm, these are all the ingredients you want to cover, right? We're going to see how the Dijkstra and Kruskal eventually will have all these corresponding ingredients. Right? Solution so far. All right, so the two things here is about ranking and also measuring. Ranking and measuring. Okay. Okay, so let's now complete. Okay, the best solution so far. Let me say a little bit more about it. The best solution right now. We call this more formally the locally optimal. Locally optimal. But not necessarily making the solution so far the globally optimal already. I'll try to draw you some correspondence maybe next time, right? So today I just want to finish the bullet point and then I can show you the one-to-one correspondence in Dijkstra next time. Let me just finish the last bullet point, okay? Locally optimal, but not necessarily is going to be globally optimal already. Not necessarily, because we still got later iterations to finish. Think about Dijkstra, for example. I just want to mention that briefly. So capital D value, if the vertex is still exists in the priority queue, we know that capital D value, it might be still subject to changes later, right? So right now, the capital D value may not be equal to little d, but it will be later. So it may not be globally optimal just yet, but it will be later. All right, last point, which is important. Greedy in the sense that I keep grabbing in each iteration some choice, but I never regret. Once a choice is made, never undo it. Once you remove a vertex from the priority queue, you never put it back, okay? Just once. Never ever undo it. Okay, never undo it. So we got basically step number 1, step number 2, and then 3, and then 4. Okay. So 1, 2, 3, and 4. So these 4 will be how you can judge if a particular algorithm is actually greedy. And of course, when you design your own greedy algorithm, just make sure you follow these 4. But I'll give you an example before you can actually be more creative on your own. Okay. Okay. I got 2 minutes. I think I can finish this part, okay? And that's it, okay? Conceptual. Let's now visualize greedy algorithm, okay? Imagine that this is the partial solution we have built so far, up to now. Maybe there are 100 iterations in total, but we have done only 50, right? Let's say we got partial solution so far. And by doing one more iteration, we basically want to extend our partial solution. Whatever we have got so far, we don't regret. We keep them. But we want to extend the solution by just one choice. So in order for us to complete the current iteration, there might be a choice over here. There might be another choice over here. There might be another choice over here. There's so many choices in general, more than one. But somehow we can choose one that's going to be the optimal, somehow, based on the cost function. Okay? So we're going to say, we're going to somehow choose. We're going to pick this particular choice. That one there effectively is going to grow our partial solutions to be something strictly larger. So this is the solution built from the previous iteration. This will be the extended solution after the current iteration. All right? And what's really important is whatever choice you made based on the cost function, guarantee conceptually, you're basically moving in the wrong direction. Okay? You're basically just contributing towards the final solution. This will be the final complete. I can draw better, sorry. Okay, let's say this will be the final solution we want to reach. This will be the final complete solution. For example, wouldn't be the case that if somehow you make the choice right here outside the complete solution and you extend it this way. In that way, you're going outside the complete solution, right? Conceptually, it's not the case, right? That's something you have to prove, right? Depending on the cases, okay? Okay. I'll leave the diagram over here. I think there's still maybe one or two insights I want to annotate the same diagram, but I'll do that on Monday, okay? Okay, so I think we got 4 more lectures for the course. We just keep going, right? We're going to cover the minimum spanning tree algorithm, its correctness arguments, and we should be able to do some dynamic programming as well by the end of the course. All right, thank you. I'll see you tomorrow in Williams Small Center.